Let's look at PLA again to see what else we can optimize. Recall that PLA does its updating by taking the original weight vector theta and updating it by adding a term which represents the input vector times its own classification, yx. This has the effect of moving theta in a direction that's going to help correct that misclassified training point. The updated vector is going to be theta prime. But we've noticed that in some cases that when we correct a misclassified example, for example, this one, and we correct it by moving it into the blue space, it could in fact inadvertently do too much correction and cause many other points to be misclassified. Can we do anything to fix that? Let's look at what PLA does to train the classifier and how it evolves over the cost function. Here, the cost function is just the change in accuracy over time as we get the training set more and more closely separated. In the green curve, we see how the cost function evolves over the iterations. It starts out fairly high, but after a while drops down as we get number of points corrected. However, at some points, we can correct a misclassification and cause the error to go up. After we run out of time, at the 1000th iteration, we might decide to stop and output the actual PLA weight vector as the model. Of course, over this entire stretch of the 1000 iterations, we've had various different theta vectors as coefficients to the input vector. We can plot how they do on the test set as well, and that's the purple curve that you see. This generates the final perceptron learning boundary. You can see it's not that great because there's obviously a better fit that we might have encountered earlier when we were at this portion of the graph. But because we ended at the 1000th iteration without the dataset being properly separated, we chose a suboptimal decision boundary. Now let's look at the pocket algorithm. I'm going to put standard vanilla PLA on the left for comparison. The pocket algorithm gets its name because it keeps a copy of the best parameters in its pocket per se, and keeps that for all of the iterations. Only when an iteration improves over the previous best does the weight vector actually get updated. So at each time step, we keep the best cost function JTrain and the best set of parameters so far. Only when we update and we find that we can actually improve that we bother to update the weight vector and our cost function. It's really as simple as that. The resulting boundary looks a lot better because we've kept the best out of all 1000 iterations.